My name is Luke Kanies. I'm the founder / owner of Reductive Labs, which is an open source software. I write open source server automation software. And if this works, which it doesn't. So like I said, I'm the author of Puppet, which is an open source tool, open source server management tool. I run my own company. Puppet's written entirely in Ruby. And strangely, I've been in the Ruby community for a while, but RubyLang is the only place I've ever been called a troll, which is strange to me. I've been trying to get Ruby talks accepted about the strange and sometimes cool things I do with Ruby, and I haven't had a whole lot of luck. So this year for RubyConf, I decided to skip the whole Ruby part of the talk and just submit a talk on things that I think are kind of cool and fun and are not necessarily Ruby specific, but are also kind of hand-wavy and not necessarily very rigorous, unfortunately. So I have a chemistry degree, and I have a severe fondness for math and math geekery, and especially the way that you can teach your brain to behave completely differently by focusing on math and the models that math brings you. So that's kind of what this talk is about, is some of the things that I've learned about math, that I've learned from math, that I don't use math to solve problems or to do design, but I take the ways that I've learned to think from math and try to apply those same mechanisms to how I think about programming. So this is the simplest example of an Epimenides paradox, a statement that inherently is a paradox. There are lots of other forms that are longer or more interesting, whatever. But this leads us to this is the first road to how we talk about Godel's incompleteness theorem. So I'm going to lead us there, hopefully. This is pretty easy. It's not interesting. It's not useful. But is it provable? And in order to talk about, I guess I didn't mention that in the beginning. I am going to talk about Godel's incompleteness theorem. I'm going to kind of walk to that. And in order to talk about that, we have to talk about provability. Lower it. Is that better? Okay. So what provability means is that you're operating in a. Should I turn it down? It only makes sense to talk about provability within a given system, within a given, the real numbers or complex numbers. You've got some set of axioms, and you're using those axioms to derive the thing that you're trying to prove. So this statement is true within English, which doesn't really have axioms, so it's hard to talk about whether it's provable or not. Before I get started, though, I want to say that I'm not a mathematician. I really only play one at night, so the two things that we're interested in when talking about Godel's theorem is completeness and consistency. Consistency means that you can't find two statements that are both provable and are inconsistent. You can't find A equals B. You can't find 1 equals 0. You can't. It's kind of the simple math stuff that you don't want to have inconsistent statements. And complete means that every true statement is provable. There are no true statements in the entire system that you cannot derive from the axioms that the system itself is built on. That's Kirk Godel, who starved himself to death because he was so afraid of the Nazis. He actually was a good friend of Albert Einstein. They used to take, I believe that they would go to work at 10:30 in the morning, take 45 minutes to walk to work, spend about 3 hours at work, and then take about 45 minutes, they'd leave at 3 p.m., take about 45 minutes to get home from work, and that was their work day. So it's not so bad. So this is Godel's theorem. It's entirely useless. It's very math. I tried to get the Greek letters correct, but I couldn't. I read 800 pages about Godel's theorem, and I still don't understand what that says. So in a slightly more useful form, it basically says that if you take any system capable of talking about arithmetic, and the way that we usually phrase this is any sufficiently complex system cannot be both complete and consistent. You get to pick, basically, but you can't have both. So he gave us this choice, and in a lot of ways he didn't really give us a choice, because if you were to ask any mathematician which you would rather give up, completeness or consistency, if you give up consistency, then you find that all of your numbers don't mean anything, because anything can mean anything else. You can find 0 equals 1, and then your whole system's kind of broken. So everyone picks incomplete. because everything else kind of breaks otherwise. So how did Godel prove this? And I think this is especially interesting for me I find this comes up a lot more in Ruby than it did in other languages because Ruby is really good at self-reference. So what he used was what's called a quine, which is a self-referential statement. So this statement is false is a quine, this statement is true is a quine, this statement is false as a paradoxical quine, and this statement is true as an uninteresting quine. So what Godel did was he came up with a really curious quine that was written in the real numbers. He did something that looked a lot like ASCII encoding, where he basically took all of the characters that he wanted to use, encoded them into real numbers, and then came up with a statement in the real numbers that said what he wanted to say. And the quine that he used is this quine. And if you can imagine this statement to be false, either way you do it, you get to, either the statement is false, which gets you an inconsistent world, or the statement is true, which gets you an incomplete world. And the statement itself is really simple. And there's no way I could ever walk through the proof of this thing. But the interesting thing is that essentially he was able to express this within the system he was using, within the real numbers, which was what this was all about. And then that he used this to create as a general system that he used. This is the first time I've given this talk, so it's going to be kind of halting. If you guys have any questions, feel free to ask questions. I'm not sure how well I can answer any questions because, as I warned in the beginning, this is a little bit hand-wavy, but I'll do my best. So if G is false, then the real numbers are inconsistent, and it all comes crashing down. If G is true, then the real numbers are incomplete, and he's made his point. And this is where it gets really interesting to me, and this is what people who talk about Godel don't often talk about, this aspect of it. But the reason this is interesting is because the real numbers are meant to model reality. The mathematicians really wanted in the early 20th century, their goal was to take the real numbers and prove that the real numbers were a perfect model of reality. There was a perfect idea of math, a perfect idea of numbers, and the system we use that we call the real numbers that has this set of axioms, that system is a perfect model of reality. And that was the whole goal of saying that it's complete, is if we can prove that it's complete, then we can prove that everything you can have happen in reality, you can also model with the real numbers. And that's really the crux of it. And the other great thing about Godel's theorem is that it's a general theorem. It's not just for real numbers. It's for any sufficiently complex system. Any system really that can do self-reference is subject to Godel's theorem. So this is how I think about the theorem. If you have a relatively powerful system, it cannot model reality perfectly. And the ways in which it will fail to model reality is through either being incomplete or inconsistent. And I think, as always, as programmers, we would always say we'd rather have things we can't model than have inconsistent results from our code. So it's not really actually a choice, but you can think of it as a choice. I like to think of it as a choice. I also came across an interesting, it's not quite a corollary, but I feel like it's kind of a corollary, that any universe simple enough to understand is too simple to produce a mind capable of understanding it, which feels like the universe itself is almost self-referential, and that it itself works along the same lines. I don't know. So anyway, so you get to pick. You can pick inconsistency, incompleteness, but I think every programmer in the room will also say you have a third choice. You can pick exhaustion, otherwise known as a programmer halting problem. So how this happened was in the early 20th century, people were getting really interested. They were talking about set theory all the time. And one of the smartest guys in this space doing a lot of the most interesting stuff was Bertrand Russell, who has written he's written great philosophy, great, I guess I would say anti-religion, and great math. So he was working on set theory, and he was having this letter exchange with some friends, and they were talking about sets of sets, and this was really groundbreaking stuff in 1910 or whatever. And it's cool, and okay, sets that contain themselves. And then he realized that there was a serious problem. He theorized the set of all sets that do not contain themselves. And the problem is, you can't have such a thing. It can't exist. The question is, rather, you can have such a thing, but does the set contain itself or not? Because if it's a set of all sets that do not contain themselves, if it contains itself, then it's not in the set, which means it doesn't contain itself, which means it's in the set. So you've got this this paradox that he encountered as he was experimenting with this whole new realm of logic. And it caused a lot of trouble because they were really hoping that the real numbers were a perfect model of reality. And if the real numbers are a perfect model of reality, then you can't have paradoxes. You can't result in these kind of conflicts or paradoxes if it's perfection. So he and Lord North Whitehead started writing the Principia Mathematica. And its goal was to get rid of this self-reference, to remove this ability to talk about yourself. And I think a lot of us are going to recognize something like this. He built these ever more complicated logical typing structures so that you could only ever talk about something that was at a type below yours. You couldn't talk about yourself, you could talk about the other things below you. And then you just kept building up and up. And he gets 3 volumes into it. And they weren't done yet. They had at least one more volume done. Of course, they think it was one more volume done, just like I'm pretty sure I've only got 1 month left for my next release, but I said that the last 3 months in a row. So they thought they had 1 volume done yet. But then Godel came along and produced this theorem basically saying, yeah, sorry guys, you can put your pens down because the real numbers are incomplete and there's no point in trying anymore. As I said, we've probably all come across these. So the real problem that he had is self-reference. That was where things got really complicated. And in a lot of ways, this is like recursion. Recursion is a type of self-reference. Things get more complicated, and Godel showed that even without self-reference, because the real numbers don't inherently have self-reference, the axioms don't talk about self-reference. You can go through, I'm guessing nobody in their high school math or whatever had their teachers talk about how the real numbers can be self-referential. You don't go into these things, but it's there if you work hard enough. So the question is, how can we use this reality, this problem that we've proven that sufficiently complex systems cannot model reality and are inherently subject to incompleteness? So one of the easiest lessons to take away is build the least powerful solution you can that will solve your problem. If you have a problem, something to model, and you build a very simplistic solution that isn't capable of self-reference, that isn't capable of arithmetic, that isn't capable of really much of anything other than solving a specific problem at hand, you're a lot more likely to actually be able to perfectly model your problem. And at least you're going to get a lot closer to it. And the nice thing about simple solutions is they can always be upgraded later to solve the problem. Another thing is that if you find yourself building infinite stacks of anything, frankly, if you keep stacking on things to try to handle complexity, the reality is most likely that you're trying to model something that isn't modelable. You're trying to find a way to make it all perfect, to make it all right. And I think you're probably wasting everyone's time, which it keeps us safe from you doing other stuff, but otherwise, probably not the best idea. So one of the things that I've definitely been confronted with in writing Puppet is the model that I'm writing, the model that I'm operating on, is not reality. And the implementation of my model is also not reality. When I look at Puppet, when I look at the problems that I'm trying to solve when I'm programming, there are always at least 3 things that I have to deal with. There's the reality that I think I understand perfectly, that I'm trying to model this reality. So I come up with a model that I think captures that reality well, and then I implement that model. And none of these things, only the reality itself is reality. Godel has shown that our implementation cannot perfectly model reality, that we can't perfectly model reality. But there's also a difference between our implementation and our model, especially if you've got multiple people where one person's writing the model and one person's writing the implementation. So seeing these disconnects and seeing what kind of limitations there are in connecting these two together, or these, each piece to its adjacent piece, there are limitations. They're not just inherent limitations, they're mathematically proven limitations, which is a very different thing than I've convinced myself. You don't need to be convinced, it's just, the universe says it's so, and it is. So one of the nice things is that you do have some power to decide how your model fails. Because you're trying to model reality, you're designing the model. You're designing how you want to model reality, and you can choose some processes to say when this fails, or the amount of incompleteness that I'm going to suffer from in my model. You have some control over that. So I come up with this a lot. So Puppet is a server automation tool, as I said. The main thing that Puppet does in its model is it tries to model the different resources that occur on, at this point, a Unix machine. So rather than talking about commands or file formats or annoying things like that, I talk about resources. I talk about users, groups, packages, services, hosts, blah, blah, blah. So Puppet actually has two realities that it has to deal with, because there are, I mean, how many Unixes are there out there in the world? I think I've got 7 platforms that I consider to be supported platforms, and I know there are, tens of hundreds of thousands more Unixes out there. So I've got the reality of the platforms themselves, but then I also have the thing that those platforms are modeling. So users are the easiest example, because almost all Unixes, probably some don't do this, but as far as I know, all of them have a POSIX user idea. And so the model that they're talking about is essentially the same model. But I still have to go, you look at Red Hat, and Red Hat has the tools around user management have this ability to manage home directories. The tools around user management in OS X don't have that ability, and they have even less ability because the tools around user management in OS X don't exist. So you have this problem of, there's a thing I need to actually model. This thing exists in some sense, but it doesn't exist actually anywhere. It's expressed in all the different Unixes as a model, and then I have to write a model that then models that expression. And then the real question is, does the user actually exist? Notice none of these are actually reality. In a lot of cases, there is no reality to the user we're talking about because it's some mental construct, it's the daemon user, whatever. But in a lot of cases, it's one of us. We have a user account that needs to be expressed somewhere, and that user account has needs, and in a lot of cases, the needs around that user account are not part of the built-in model, and so we have to see that just trying to model their model doesn't work, just trying to model reality doesn't necessarily work. And as I said, there aren't solutions to this problem. It's a proven thing. You cannot perfectly model it, and so you have to decide how you're going to work around it. I'm going far more quickly than I figured would happen, so one of the things, I'm going to try to talk some about some of the things I use to, I've talked a little about how to deconstruct models, how to make it more difficult to model things, and how your models will fail. So hopefully I can provide some ideas I use for how I go about making modeling decisions. And I'm not going to say that I'm an expert modeler or whatever. I'm a sysadmin by trade. I'm just faking like a programmer. So there was an Indian, I think he was a mathematician, but he worked in chemistry. That's much better. So, name of Ramachandran. I think he had other names too, but I don't know what they are. And we're going to use Ramachandran and his work to fight math with math. So, what Ramachandran taught me how to do is to think of making a decision. Think of making a design decision or of changing your model as the difference between...
You're losing your mic.
He turned it down, and apparently he turned it down all the way.
It's not facing your mouth.
I
know it has to.
It's okay.
Yeah.
So let's go ahead, better than feedback.
Is that good?
Yeah.
It's fine.
All right. Not good with tools, obviously. So to think about decision making as the difference between potential energy and kinetic energy. When you're on a hill, if you think about walking along a ridge on a mountain, you're at a very high potential energy. You roll down that hill, and the process of rolling down the hill and all the sticks and twigs you run into is converting potential energy to kinetic energy. So if you think about applying this to program modeling, if you have made decisions, if you have a bunch of decisions to make, you're trying to figure out what your model is, you're in a state of very high energy. You're under stress, you have a lot to do, and you don't know what you're doing yet. You haven't made decisions. That process of having not made decisions, that state, is very high energy. It's expensive to stay in. But when you go down, you make all your decisions, you're in a very low energy state. You've got no decisions to make, you're very comfortable, you're happy, there's nowhere to go from here. So what Ramachandran did was he came up with a way of plotting the kinetic and potential energy curves. This is a pretty bad graph, because it's not understandable by anybody who's not a chemist. But what he did was he was talking about the bonds between two peptides in a protein. So you've got two proteins or two peptides in a couple hundred peptide protein, and as they rotate along each other, they encounter different levels of energy, different levels of potential energy. And sometimes you have a very high potential energy. It's very difficult to rotate this way, but maybe it's very easy to rotate this way. And what he found was, as he mapped out the different energy curves for each peptide bond, he was able to discern the structure of the proteins themselves. So beta sheets and alpha helixes are two of the main structures are the only two structures you're going to find in DNA, the secondary structure, I think they're called. And pretty sure they're secondary. And so what he found was that you could actually take this calculation of the potential versus kinetic energy and turn that into figuring out the structure of the protein, which was really interesting. But the thing that I found interesting was that there are often, as you think about this model of moving from one low potential energy state to another low potential energy state, there often is a peak between here and there. If you're in a valley, you will often have to go over the potential energy peak, otherwise you can continue going downhill. So I'm not doing a good job of explaining this. I tried to find a better graph that would actually show what I was talking about. But if you're in a high energy state, if you're at a point where it's difficult to maintain the status quo, then it is very expensive. It costs a lot of energy. It costs a lot of mental processing power. But the nice thing is that you can see all the places you can go from here. You can actually assess what low energy values are around you, and it's really easy to make low cost experiments that kind of dip your toe into the valley without going all the way down. And one of the really cool things about this state is that everywhere you go from here is lower cost. If you're at a point where you haven't made decisions, where it's very expensive to stay there, you can always make it pretty easy pretty quickly by just making some decisions when you have the need to. So the thing about low energy states is that they're really easy to stay there. Once you've made all your decisions, or once you've got a decision made, it's pretty easy to stay there. The problem is you don't have any perspective. You don't know if you've made the right decision. You don't know if there's another decision you could have made or another lower energy state right next to you. And the only real way, if we, again, continue to follow the fake 3D mountainous model, the only real way to know if the next valley over is deeper than the one you're in is to climb back up on the mountain. So there's a lot of cost to making a bunch of decisions early and sticking in that, getting into all these low energy states, especially every decision you make has the same kind of conflict. Do I want to get into a low energy state right now and stay there and hang out, but not be very flexible, be very rigid, and have it be extra expensive, because converting from a low energy state to a high energy state is far more difficult than just staying in the high energy state in the first place. If you're on the ridge and you climb down and climb back up, that's a lot more energy than just staying on the ridge. And again, every change from your low energy state is harder to do than your current state. You can't say, this isn't working, and then spend a little bit of energy. You have to spend a lot of energy to get out of that state again. So how I didn't do a good job of connecting this to Ramachandran, but it meant a lot to me when I was 19, and I think I've lost a lot of understanding of Ramachandran, and I'm abusing it a lot. But the way that I think of the plot and what he's showing us and the curve of this interaction of this bond is that it's all about energy deltas. And unmade decisions are very high potential energy, but made decisions are very low potential energy. And many unmade decisions are expensive but flexible. You can stay along this peak. You can look down into the valleys. You can even kind of dip down a little bit without going all the way down and learn a lot. And this is, I'm sure all of us have gone through this when we're trying to model something. You try a bunch of different things pretty quickly. You try to make as few decisions as possible up front, and you go through as many different forms of the model as you can. And then the most decisions made, if you've got it all figured out, if you're confident it's all working, it's very cheap. It doesn't cost you any energy to stay there, but it's very hard to change things. So if you look at connecting this with Godel's theorem and with the incompleteness there, you'll find that if you make a bunch of decisions now and you find that your model is not matching reality in the way that you wanted it to, which is to say, your model will not match reality. We know that. So how can you match your model match as well as possible? One of the ways you do it is you don't make decisions up front. You stay in the highest energy state possible because, again, you're going to fail. If you make all your decisions, you will not match reality. You know that. So instead of saying, I'm right, I'm just going to stick with this, if you wait as long as possible to make your decisions, then you have a much better chance of making the right decisions about how to fail to match reality. Because that's really what it's about. So you'll have a lot more knowledge when you do have to make a decision. And you'll always have ways to easily reduce your energy state. And the nice thing is, you won't make those decisions until you need to. And when you need to, you'll be in a much better position to say, this is how I want my model to match reality. Or this is the way I can afford this to be wrong, but this part has to be right. If something is pushing you towards making a decision, then most likely that's a part of your model that you really do need to have to make a decision about. And this does start to sound like Agile programming. Delaying decisions, doing fast iteration, things like that. But you got to admit it sounds a lot cooler when you're talking about mathematicians. So probably most of us know what asymptotes are. They're curves in math that you can approach an asymptote. So if you've got a line and an asymptote to that line, the asymptote can get infinitely close to the line but can never actually reach the line. So we know that we can't match reality perfectly. But we can get arbitrarily close to that. We can come really, really close, and we can probably refine our model infinite number of times and get ever closer, ever closer, ever closer. So you can asymptotically approach it. And thinking about it like that, I've found really helpful because I know that it's just a question of refinement. Because I know there's no perfection, because I know there's no there, the best I can hope to do is very small changes over time. And again, this is all about model iteration. And when I started reading the Agile books a number of years ago, it made a lot of sense. But to me, I always directly applied it to this idea of approaching the asymptote. And I just reread the abstract that I wrote for this talk, and I did actually talk about fractals in it too. So one of the other ways that I think about it, fractals are really interesting. And I chose a fractal appearing in nature. This is broccoli. Most of us are probably used to the fractals that we see from the math algorithms and stuff. But fractals appear in nature all the time. If you're flying, you'll see clouds, and you can't tell how close the clouds are because the level of detail doesn't change as you get further or closer to the clouds. A lot of nature is like this. Ironically, mountain ranges are very similar too. So you could tie it all back to Ramachandran again. But as you get to the parts of your model where you have to spend more time on. So I like to think of myself as a squeaky wheel developer. I spend time on the parts of my tool that people complain about. If no one is using a given part of the tool, or if I've got hooks to add functionality, but no one's ever asking that for that functionality, then I'm not gonna spend time there. And spending time, another way of saying that is I'm not gonna make that a higher resolution model. So when I go and I spend time, sorry, I've got a definition here for you. When I go and I spend time on a portion of my model, then I'm making my understanding of that model higher resolution. I'm getting more and more detail. And I'm going to get closer to that asymptote, but of course I can't ever get quite there. So when I think about designing my models or coming up with the models for the programs that I'm working on, I definitely think of it as it's not just a question of iteration, because iteration implies you've got a thing that didn't quite work, you replace it with another thing that didn't quite work. But really it's a question of you draw the skeleton, and then you go to the parts that matter the most. You go to the parts that are the highest impact, that you get the most feedback from your customers, so that are going to make you the most money right away. And you make that a very high-resolution portion of your model. And you make a lot of decisions there because you have to, because you can't really write much code without making some decisions. But the parts that don't matter, or that don't need to be high resolution, you leave those at a very low resolution, and they don't come very close to approaching the asymptotically perfect idea of the model that you're trying to match. So we can get much closer, but you're still bound to failure. I was afraid this would be what we were talking about. So for me, the conclusion is that math hurts your brain in really interesting ways. Many of you have probably read or at least heard of Douglas Hofstadter's Godel Escher Bach. I read that after college, and it was like the end of a 3-year funk for me of not thinking very much, and Godel convinced me that, or Hofstadter convinced me that thinking could actually be fun and very different again. And reading that book will definitely break your brain in really strange but really, really cool ways. And even the people I've talked to who have read it who didn't understand it still really enjoyed it and still got a lot out of it. It's interesting talking to people because most people, you can get 2 people in the room who read it and are absolutely confident they understand it, and they will say completely different things about the book. They got completely different things from it as to what it was actually saying. And it does provide different ways to think about the problems. I think the Agile stuff is really interesting, but I think it's a little bit, for me it feels a little bit too direct. It's a little bit too, here's what you do, but I want ways to think about the process. I want other ways to reframe problems that I have. I can't remember the guy's name, but there was a famous algebraist who, I think the phrase was invert, invert, invert. So in algebra, you often have a problem that is intractable in the form that it's in, but if you can convert that problem in some way, even multiplying both sides by 10 or multiplying both sides by x, will have these really weird repercussions on your ability to solve the problem. So the first step towards solving the problem is making it more complex. But that's another way of thinking about the world. It's another way of thinking about that problem. And if you've never done this in algebra before, if you're solving algebra and you've never had this idea of first let's make it more complex, then when you first come across it, it's like this fabulous tool that had never been there before. So I'm always trying to find ways in science. I read a ton of science stuff. If you guys aren't reading Seed magazine, you really, really, really should read Seed magazine. Finding science stuff, math things. I always find things outside of computers that I can use, but especially science and math because I like them most, and they make me sound the smartest, except when I'm on stage, to just give me new ways to think about problems. And I do my best to abuse the ideas that I get from those fields and apply them to computer problems. I seem to actually be out of slides, but are there any questions? Sorry. And the subtitle for Godel talk is The Eternal Golden Braid, which has the same acronyms. And then he had, for the cover of the book, he had an interesting, a single block of wood that you could shine light on from 3 different directions that would show the different letters. So very self-referential kind of funny thing. It's a fun book. Half the book is set up to be dialogues. So Zeno's paradox, one of the original paradoxes, one of the first people to ever talk about paradoxes was the Greek mathematician Zeno. And he had what I think was the paradox of motion, which was basically that in order to get from point A to point B, you first must travel half the distance, and then you have to travel half that distance and half that distance. And essentially, you can never actually get there because you're always only traveling half the distance. And Lewis Carroll, in a story about a race, and so the example that Zeno used was Achilles, the fastest man alive, or that ever lived or whatever, racing a tortoise, who clearly is going to be slow. So Zeno had this, and Lewis Carroll actually wrote that up as a dialogue, as a conversation between Achilles and the tortoise about this race. But it was after Achilles had obviously won the race. So what Hofstadter did is he took that idea of the dialogue and he made half of the book. Every other chapter is a dialogue between Achilles, the tortoise, a crab, and my personal email is luke@madstuff.com. The crab's house is the crab's mad stuff. So that's what it is. So it's a conversation with all these characters, and he'll use the dialogue to introduce these kind of complicated mathematical ideas, often in very strange ways. So one of the things that he used to talk about how you cannot model reality perfectly was there was a bet between, I believe, the tortoise and the crab as to whether a record player could be built that could play any record. And the problem is that every record is something physical. Every record player is something physical, and if it's physical, then it's subject to vibrations, which means that you can find a specific tone that you can play, you can put on a record that will cause the vibrations that will break that record player. So there's this, a record player tries to model reality. Everyone knows there are these hi-fi, really expensive audiophile equipment you can do. And what are they trying to do? They're trying to perfectly model reality. They're trying to get the exact same sound that you would get from being on, at the show, listening to the band. But you can't. The same theorem that works here it's just as true in anything that has self-reference. And because your record player is producing sound and is a corporeal thing subject to sound, it's also got self-reference. So you can always, for any record player in the world, you can create a record that will destroy that record player, or at least is unplayable on that record player. So he would go and he would introduce these kind of really difficult ideas with really straightforward things that you could, really straightforward is a stretch, I say, but with interesting things that were not math related, but were instead something very different. And then it would be complicated math stuff from then on out. So I will actually answer questions now. There were some up here.
So anytime you're modeling something and you try to increase the resolution, it's a bit tougher. Each time you try to get closer. And a common example in software is the Chrysler compensation thing, where they were building. They wanted to get timesheets and figure out how to pay employees, right? And instead of directly modeling the problem, they used metaphor, and had parts, and you basically assemble the compensation thing to parts. And I'm wondering if you think it's useful sometimes to, instead of trying to directly model the problem domain, you use metaphor instead. And when you think, what are the trade-offs, and when might you want to choose metaphor instead of directly modeling it?
I definitely like metaphor. I mean, I'm really using metaphor to talk about programming, so I'm a big fan of metaphor. I think the trade-offs are, it's really a question of how successful you can think about your model, and then how successful you can share that understanding. So if you're working on a team, it's not just critical that you have a good model, but it's critical that everyone on the team has not just the same model, but the same understanding of the model. And one of the problems we have in computers is that we're often dealing with very abstract things that don't exist in reality, or that barely exist in reality. There's a user in reality, but the problems that are around that user are all digital, they're all software, so it's hard to talk about them in reality. So coming up with metaphor that does a good job of explaining the model in a way that everyone in the team can understand and can really get behind, because humans understand metaphor really, really well, then you can translate the metaphor back into reality, into a model. Of course, at some point you have to write code, and it's hard to code the metaphor. So talking about metaphor is great, and writing a metaphor, but then when you have to translate that into a model, you don't have to convert back to non-metaphor. Another question?
Yeah, I had a question about modeling again. So, one approach you mentioned is make it as simple as you can. And there's a lot of advantages to that. But that often leads to sort of many small models that don't interoperate well. Wanted to see your thoughts as to maybe shared domain models that we can tap into, such as microformats, such as WordNet, that sort of thing.
Right. So I think it was Einstein who said that everything should be as simple as possible, but no simpler. And I certainly can't recommend that you take a model and unnecessarily simplify it. But I know at least I have the tendency to overcomplicate things. So fighting that tendency is an important thing. So in terms of providing shared models, or, the easiest way to talk about having lots of small models interoperate is through some sort of API. And if you've got a good model and it's very small and it's very self-contained, then you can usually come up with ways that it makes sense to talk about that model from the outside.
API, you know what I mean? It's an explosion problem to get.
You have that anyway. If you look at, if you have a good unit test that just tests a given class that you're working with, and you've essentially mocked out all the other classes you're interacting with, then what you're doing is testing what you consider to be the API between that class and the classes it's interacting with. You do have an API. Even if you think of it as one big model, you've got 1,000 classes, each with their own API. And you've got private methods that are not considered part of the API and public methods that are. You have to decide, am I going to think about every one of these classes, every one of these models, as a standalone thing that has these very few attachment points? Or am I going to just line up all my classes next to each other and slide them into a deck of cards so that they're all touching all over the place? And that, I started to write like that, and it's very difficult. And as I've gotten more to the point of having, as much as possible, all of my classes be independent models that are meant to model something well and have very few attachment points, my code has gotten much more maintainable, and I can understand it a lot better, which is obviously important to me. But so the microformats thing I think is really interesting, because one of the things that does is it provides you the ability to share models across lots of different systems. And that's one of the things that's really missing in today's computing world, in most cases, is all the things that we talk about. Humans, we all know that they exist, and we usually write software that does the same thing with them. We might all of our software has a user. All of our software has these sessions and things, but there isn't much sharing. We all know what a calendar event is. We all know what a task is. So one of the things that there's no shared model for right now, and maybe this is starting to change, but I've got like 7 applications, 7 websites that I use regularly that all have task lists. So now I've got these task lists scattered all over, and so the process of making sure that I get crap done every day is go to each of the stupid task lists. Because they don't have a shared model, because they can't share this information, they don't have a way to talk to each other. And if you were to go to create a shared model for those, what you would find is that most of them have a slightly different idea of what it means to have a task, which is obviously annoying, but the reality of things. So as we've gotten better about sharing calendar events and sharing V cards and things like that, we've kind of had to settle on, yes, that's an imperfect model. V card is an imperfect way to talk about humans, to talk about contacts, but at least everyone's agreed on it with that and deal with the repercussions. Either Question?
The power of the model is in its simplification and separation from reality, like a map. That's why Google Maps doesn't only have the satellite view. Yet, in your asymptotic way that you're thinking about improving your program all the time, what about the fact that the reality is a moving target, and in an asymptote, aren't you sort of freezing that target and trying to get to it? Dealt with that moving target idea?
Yeah, definitely. And it's easy to find yourself spending a lot of time iterating at a high resolution, trying to get much more detail, and finding that while you're doing that, the large-scale detail is changing. And so what you need to do is move up in detail, go back to a low-resolution mode, reassess whether, I'm trying to fill out this skeleton, but has the skeleton moved since I went and started working on the fingers? And I think the only real thing to say there is that it's not safe to stay at a single resolution all the time. And I think this is one of the things I really like about viewing it as a fractal work, is that if you're only ever at one resolution in your program model, then you aren't getting a good picture. And this is, we all have these high level and low level and detailed discussions. Well, I think of those as being resolution. And you have to go up in resolution and down in resolution. You have to get to the 30,000 foot view. And then sometimes you have to get on your hands and knees and dig through the dirt. So you don't have to shape for those resolutions and deal with it when the reality moves. That asymptote will move. I agree. It's going all the time. And so you have to do your best to follow it. And sometimes if it's moving like this, then you can follow it with very small changes. But if it moves drastically, then you have to step up a lot, refactor at a very high resolution to try to match that move. Question?
When you're trying to sort of model, again, your software against reality, is it more important with all of your sort of model within the system that they're more accurate or precise in terms of the mathematical definitions of accurate and precise?
The question is whether it's more important to be accurate or precise, and the definition of accuracy is that you'll get a good, if you're shooting for the bullseye and you're very accurate, you'll get a good grouping around the bullseye, but you won't necessarily hit the bullseye with any of them. If you're very precise, then you might get up and to the left, but every dart's going to be very close to each other. So you're getting in the same spot every time, even if it's not the spot you're aiming at. I think it really has to depend on the application you're writing. I know for me, for the code that I write for Puppet, I'm modeling resources, and in general, people aren't doing very complicated things with those resources. So it's much more important that I get a rough target, that I get a chalk outline of that resource, than that I get all the little details. Especially since I can come back in, you can do squeaky wheel development. If you focus on accuracy, you can do squeaky wheel development and say, here's the chalk outline. If I find that people are really dissatisfied with the lack of resolution in that outline, then I can come in and fill more detail. But if you spend a lot of time working on precision, then you've got a lot of detail already. And if somebody says, it's great that you're getting really close, but I really would like you to hit the bullseye once in a while, then you have to refactor the whole problem. So I generally focus on accuracy first and worry about precision when somebody really, really cares about precision. But it definitely depends on the application you're trying to model. Other questions? Okay, one about quarter till anyway, so I'm just about out of time. Finishing early, which I think is rare for this year's RubyCon. Okay, feel free to come up and bother me afterwards.